Okay, so this is this talk is in. I was realizing that it's been a good 10 years that a group of us have been thinking about theories of 2-1 factors, going back to papers of Ilias and mine with David Sherman, and Isaac Goldbring's been involved, and Thomas Sinclair. I can't even. I apologize for all the co-authors that I am not acknowledging. There's a long list, but this has been an ongoing project, and a variety of different connections between operator algebra and this field of continuous logic have come up over time. And one direction that Isaac and I looked at a few years ago, when the article got published in the Bulletin of Symbolic Logic, looked at the computational strength of the Connes Embedding Problem. And it's very much tied up with the universal theory of the hyperfinite 2-1 factor. And I want to try to say something about that in this talk. Okay, so let me give you a brief outline. I'm not expecting, so that was for people who knew what all those words meant. Here's the brief outline of the talk. There can be no talk of this kind in which I do not remind people of what continuous logic is. Every time I try to give such a talk, I think, maybe this time I can skip it, or maybe this time I can say less about it. But then I realize I'm making use of a variety of things, so there'll be some reminder of what continuous logic means and how it applies in this context. I should also say what I mean by decidable in this. That's slightly different. Even logic audiences would be, they wouldn't be surprised at the answer, but it's not the usual answer that you would get when you're talking about ordinary classical first order logic. And then I'd like to draw out this connection with the Connes Embedding Problem that I mentioned a minute ago. And I'm just going to acknowledge repeatedly throughout this talk that there is no way that any of this is being done without this beautiful recent work, MIP RE. Henry Yuen gave the opening talk for this conference, and we lean on this result quite heavily. But I think it turns out that this actually has an impact which, I'm getting ahead of myself, but I just got to acknowledge right here and now that this is all kind of icing on the cake, and the underlying core of this is the MIP RE paper. So, okay. I'll try to give you a sketch of the proof, a few slides on how this works, and if there's some time, I wanted to make a few additional remarks. Okay, so let me just make sure I haven't forgotten anything. Nope. Okay, so I always try to do this. One slide on continuous logic. Everything you need to know about continuous logic in one slide. Okay, so just to make things easy, I only want to talk about continuous logic for a tracial von Neumann algebra. So I'm not going to discuss all the bells and whistles that go into just an arbitrary, continuous logic setup. So what's a tracial von Neumann algebra? It's a pair, von Neumann algebra M together with a faithful normal trace on M. Okay, so we fix, right? We fix the trace. If it's a factor, then of course it's a 2-1 factor, then the trace is unique. But I'm going to be talking about situations where possibly the trace won't be unique. Okay. All right. So I'm only going to talk about continuous logic in that setting. So what does continuous logic look like in that setting? Well, the setup for if people are more familiar with classical logic, we want to have operations, functions, and relations. In this case, the function symbols are the ones you'd expect them to be. You have plus and times and the adjoint. You have scalar multiplication by complex numbers. And the only relation you have around is the trace. Okay. there's one little thing that's lurking in the background, and I'll just say it by saying that we really want to consider, whenever we consider a variable in this logic, the variable comes with a bound on its operator norm. Okay, for those who know what I'm talking about, this is where I'm discussing sorts, but don't, just in this context, what we're doing is demanding that our variables are bounded in operator norm. All right, so again, moving in parallel to classical logic, you would have your atomic formulas, which you then can put together using connectives. What do the connectives look like in continuous logic? Well, I'm going to be very generous here. They're all continuous functions. So my connectives are just any old continuous function, and I apply these continuous functions to atomic formulas. Okay, so we'll see that this generosity is, you have to be a little careful with this generosity, but for the time being, that's what we do. So for instance, and this is going to matter in the talk a little bit, so I thought I'd just give you an example of how this works. If I have a Tracial von Neumann algebra, then I do have access to the standard representation of that, that von Neumann algebra. L2 of m tau, so that would be just, do GNS on M, complete it to a Hilbert space. And we know there's an inner product on this. And what is the inner product? Well, the inner product is actually given by formulas in the language which I just described, right? Tau of y star x, that's the inner product of x with y. That's an atomic formula. If you want to see an example of a connective being used, if I want to compute the 2 norm of x, then I can take the square root of tau of x star x. The square root is the continuous function being applied to tau of x star x is the atomic form. Okay, so among various things, we can form formulas of different kinds. The last thing that, if we're paralleling classical logic, the last thing is quantifiers, and the quantifiers in this case are supremum and infimum, so sup and inf. I demand, though, that when I take the sups and infs, I range over variables where the operator norm of the variables is bounded. Okay, so this is critical, and let me say why this is critical right now. And of course, when I was making these slides, I realized I need 2 slides. Okay. Yeah, so let's just point out some things that maybe when I interpret these formulas in Tracial von Neumann algebras, the formulas do not interpret as true or false. They give me values, they give me real numbers as values, okay? And that's important. We're not in a 0-1 situation. We are in a situation where the formulas are taking on real values as I interpret them. In particular sentences, that's something that is just, without any free variables, just something where I'm saying something about the object at hand, the Tracial von Neumann algebra at hand, and every sentence will be assigned a number in a Tracial von Neumann algebra. Okay, it's one of the reasons I keep mentioning this bound on the operator norm is that if I bound the operator norm of variables, then every formula becomes a uniformly continuous function on its domain. Okay. Why is this important? You'll see when it's rather important when we start trying to approximate things down the road here. If we know the form of the formula that we're trying to approximate, then since that will be values, the values of that formula will be, some collection of real numbers, and that function, the formula, will be giving us a uniformly continuous function. So if I want to approximate the range within epsilon, I'll have a specific delta that I'm trying to approximate the domain on the domain side. Okay, so knowing that we have uniform continuity for these formulas is going to be sort of critical in doing the kinds of estimations that I'll talk about in a minute. Right. So in some ways, this subject, the continuous logic or model theory of operator algebras, I think is what we've been calling it, got started with this theorem of Ilias and mine and David Sherman. And here, I want to say it this way because this is the way I'll need it in this talk. There's an explicit axiomatization in continuous logic of the theory of Tracial von Neumann algebras and also the theory of 2-1 factors. When I say explicit, I mean you can literally write down the axioms, and if you need to, I mean it's not a finite set of axioms, but you can write it down in a perfectly decidable way. And you have access to that. Okay, so we did that. We wrote it down, and we had this series of papers, Model Theory of Operator Algebras 1, 2, 3, N. And I think this might have been written down in 2.
Sorry, Brad, sorry to interrupt, but
yeah.
This was actually proved before by a group of people. I mean, there was this note by. Right, I guess
yeah,
certainly there.
Certainly, certainly this was not a surprise. I think that this isn't a surprise. I mean, there was the note. Let's see. Yeah, actually, people who might be here, right? There was a note that came out of an Ames. Was it an Ames seminar or an Ames session?
It was in 2006.
Right, Ward Henson, Marius Junga, and was there someone else, Ward? Are you there, Ward?
Ty.
Yeah, I said it, Ty. Is there someone?
And
Alex?
Jean Reno.
Oh, Reno. Right. Yeah. The only distinction I would be making here is that we in the way we wrote this down, at least the way I'm using it today, it became extremely clear what the language was, what the sorts were. This is really a recursive axiomatization, even decidable axiomatization of the theory of Tracial von Neumann algebras and 2-1 factors. So, and that's the way I want to use it. Okay. Are there other questions on this point? Okay. All right. So, all right, where are we going here? All right. So that's really all I'm going to say on continuous logic, and in fact, this theorem is going to be, is going to play a kind of an important role in a funny way in what we and what I'm going to tell you in a minute. All right, so now I'm talking about the universal theory. So what is a universal sentence? Well, it's one that looks like this. So in continuous logic, you talk about universal sentences. That's kind of stealing language from classical first order logic, where the universal quantifier is for all and the existential quantifier is the backwards E. So a universal sentence, the soup is going to count as the universal quantifier. So a soup sentence has the form soup sub x, phi of x, where the x is a tuple of variables. Remember, my variables are coming with bounded operator norm. And my phi is just some formula that has no quantifiers. Right, so what is that? That's going to be a continuous function, which is going to be applied to the traces of some collection of star polynomials, okay, in the variables that are at, the x variables, okay? So that's the form of a universal sentence. And let me quickly say, why do we care? Why do we care about universal sentences?
Just to be sure, so you said earlier that, for example, you'll be doing like supremum over the unit ball or something like this, right?
That's right. That's right. So the variables, when I introduce that x, implicitly the variable comes with a bound, and so yeah, it could be the unit ball. In fact, because everything is completely scalable, I could change my formula. I could change my bound, whatever. You might as well assume it's the sup over the unit ball, right? Just by applying a different contiguous function to the formula involved. Okay, so all right, so why are we interested in the universal theory of R? Well, okay, so when I say the universal theory, I mean if I give you a 2-1 factor and I ask you for the universal theory of that 2-1 factor, I mean tell me the real number that universal sentence takes on in that 2-1 factor. So the universal theory of R is specifying for every universal sentence the value that universal sentence takes on. Okay, and again, following up on Ilias's remark, any model theorist that would know all the words would guess this was true. so I'm not going to attribute this theorem to anyone, but the Connes embedding problem is equivalent to knowing that all universal theories of 2-1 factors are actually the same. So no matter what 2-1 factor you chose, you look at the universal theory of that 2-1 factor. If the Connes embedding problem was true, then you would have the same universal theory. Okay, so and just a reminder, the Connes embedding problem is the statement that every separable 2-1 factor actually embeds into R to the omega. And I guess, is Aaron on this, is out in the audience somewhere? Because I appreciated the fact, Aaron, that you used a U the other day for your ultrafilter. So I thought I would respond by using an omega. So
I used omega.
Somebody used a U, didn't you use?
Yeah, someone else used U, but it wasn't me.
Oh, maybe it was Andrea. Okay, all right, okay. Then I take it back. I'm gonna edit my slides right now.
No, I appreciate that you used omega.
Yeah, it's also just our omega embedding is so embedded in the literature that it would look weird if I put a U here. So okay, all right. And I think it's sufficiently important. Let me explain why this theorem is true to those people who are not model theorists who work in continuous logic. Okay, so here's a quick proof. I'm going to go from left to right. So assume the Connes embedding problem holds. This is all kind of weird to be saying this. We know the Connes embedding problem now is false. So, but I'm saying assume it holds. But okay. So every universal theory of 2-1 factors has a separable model. That's just the Downward-Lowenheim-Skolem theorem. So if I have a separable 2-1 factor, it's a 2-1 factor. So R embeds into it. And now if the Connes embedding problem were to hold, then N would embed into R to the omega, right? So I'd have this picture. I don't know if you can see me, or whether you're just looking at my slides, but you have R, N, and R to the omega, okay? And you're dealing with a sentence which is a supremum, okay? So if I start evaluating that in R, right, the value of that thing just gets larger when I go to N, and it gets larger still when I go to R to the omega. But R and R to the omega have the same universal theory. So the universal theory of N gets squashed in between. There's nowhere for it to move. So N would have the same universal theory as the universal theory of R. Okay. Going from right to left is even more fun because it's just a general fact about continuous logic that if you have all your universal theories are the same, then so are your existential theories. Those are sentences of the form imp sub x, phi of x. And if you stare at this long enough, you realize that this would mean you've got the microstate conjecture holding, right? You know, you can approximate any finite amount of information, quantifier-free information to within any epsilon you want that is holding in some 2-1 factor, you can approximate it in R, right? And that the microstate conjecture is equivalent to CEP is well known. Okay, so the interest in the universal theory of R is because it tells you something about CEP. And as I say, that was something which was known and has been percolating in the background for a while. Okay. All right. So I should say what I mean by decidable here. Let me start by saying what I don't mean by decidable, right? You could ask whether or not you had an algorithm which determined for any given 2-1 factor the exact value of any universal sentence in that factor. I'm setting up a straw horse because this is way too strong. We've been extremely generous about what we mean by sentence. We allow all continuous functions as our connectives. We're allowing arbitrary real numbers as our as the values. So there's no way you're going to get some, say, at least theoretical computer algorithm that's going to tell you the exact real value of some, some sentence, particularly some sentence which is using some incredibly complicated continuous function. So what we're really going to want to do, and this will turn out to be enough, is that we could ask for an algorithm which, given a universal sentence, and I'll say something more about this in a second, and give some tolerance delta, would produce the value in R of that sentence up to delta. Right. So, okay, so now you can start to believe that at least this is something that falls in the realm of ordinary, the ordinary discussion of decidability, right? You could, since I'm approximating the value of a sentence, I don't have to use all continuous functions. I could use polynomials with rational coefficients. Of course, the arbitrary delta doesn't, I could ask for the value in, say, any rational interval. So the number of questions that this algorithm would have to answer would be, say, there'd be a countable list and perfectly constructible countable list of questions that this algorithm would be asked to solve. And this is the way that I want to talk about decidability. All right. So it's a sort of approximate decidability. But of course, if you knew the values up to delta of every universal sentence of the kind that I just described, then you would know the value of all universal sentences in R exactly. Of course, you'd have to know all the approximations. All right. Okay, and so now comes the connection that I want to exploit. Is this? All right. The connection to CEP. All right. So this theorem sounds again a little weird, and it is particularly weird because the assumption is if CEP holds, which we know it doesn't, then the universal theory of R is decidable. So let me back up and say what I really mean here. A few years ago, like I said at the very beginning, Isaac Goldbring and I wrote a paper in the Bulletin of Symbolic Logic in which we examined the computational strength of the assumption of the Connes Embedding Problem. Okay, and this is maybe the one of the easiest theorems in the paper, but we didn't, of course it would have been great if we could have resolved CEP at that point, but that's maybe was asking too much. But just understanding the algorithmic power of CEP. So let me explain why this theorem holds as stated. Suspend belief for a moment that you know that CEP is false. Okay, so as we said, CEP is equivalent to knowing that all the universal theories of 2 factors are the same, okay? I also told you earlier that we know an explicit axiomatization of the theory of 2 factors, all right? Now, I didn't say, but it's probably not too surprising to learn that continuous logic has a proof system. Actually, one was written down explicitly by Ben Yakov and Pedersen. And what will that proof system do? It will try to construct approximate, try to compute for you the approximate values of sentences, starting with some axioms, and the conclusions will tell you this sentence is, the value of this sentence lives in some interval. So what do we have? We have an axiomatization of 2 factors, and we know that every 2 factor has the same universal theory if CEP holds. So the ordinary completeness theorem, right? This is one of these annoying logic theorems, right? Where what we're going to do here is we're going to just sit and watch an automatic theorem prover start proving everything that you can prove from the explicit axioms of 2 factors, and just wait. There's only one universal theory, so eventually this theorem prover will tell you, up to whatever delta you want, the value of any universal sentence you want. Okay, it's a dumb algorithm, I grant you that, but it's an algorithm, and it works, assuming CEP.
Oh, modulo delta, right?
Modulo delta, that's right. So that's what I'm going to mean by decidable here, right? So if I hand you a universal sentence and a delta, I would like your algorithm, whatever it is, to give me back the value of that sentence to within delta, and that's what, under assuming CEP, that's what this automatic theorem prover would do for you. Notice there's no promise that it will do it in any timely fashion, but it will. It will eventually stop, and it will tell you the value to within delta. Okay, so now I want to point out, let's read this in the contrapositive. If I knew the universal theory of R was not decidable, then I would know that CEP fails. Okay, so let's understand right now why we know that CEP fails. I'm more or less just going to repeat what Henry Yuen said on Monday. We know that CEP fails because the results from the MIP RE paper implies that Cyrilson's problem doesn't hold or is false. And that by work of Fritz and Junge and Ozawa, we know the Cyrilson problem is equivalent to QWEP. So we know QWEP is not true. And the equivalence of QWEP with CEP was known to Kirschberg. Okay, now there's a lot of beautiful operator algebra happening in there as you go from this quantum complexity arguments all the way over to CEP. But this is a direct way to get the failure of CEP. Prove that the universal theory of R is undecidable, and then you go directly to the failure of CEP. And okay, now I'm not promising that I'm bypassing anything in the MIP RE paper. It requires that, but this arc that goes through the operator algebraic results, it bypasses that. Okay. All right. So so let me try to give you a hint, at least, of why I think the universe, and Isaac and I think that the universal theory of R is undecidable. Okay. All right, so I have to tell you, I have to repeat a little bit of what Henry was saying the other day. So there are these quantum correlation sets. Now, okay, I'm going to just freely admit right now, I know very little about quantum mechanics. I know little about quantum complexity. What I know about it, I've learned by, I didn't say this at the beginning, but you could almost subtitle this talk, What I've Done During the Great Hiding. You know, since we went into lockdown in March, you know, you have to do something to stay sane. So I was reading the MIP RE paper. Yeah, although it's interesting to think whether or not reading about quantum mechanics is a sign of sanity, but anyway, that's something entirely different. Okay, but anyway, these quantum correlation sets, I hope this shouldn't differ from what Henry said, because it should be exactly the same. These are, you know, all right, I'll just read the slide. You form an NK by NK matrix using these collections of positive contractions on two Hilbert spaces, HA and HB. It's known that, you know, you could require these things to be arbitrary Hilbert spaces. It's known that that you can get away with finite dimensional Hilbert spaces to make this definition. So I've embedded that in the definition. Usually you would say Hilbert spaces, and then you would acknowledge that you could use finite dimensional Hilbert spaces. And then you take a unit vector from the tensor product of those Hilbert spaces. Oh, sorry, I forgot. The positive contraction should various for every X and Y. You should have, oops, did I say that wrong? I did, sorry. That should say for every X and Y, the sums are 1. So you have, right, so I think Henry said it well on Monday. For every input X, right, you have a probability distribution on the outputs, which are labeled by the A's. Same with the input Y, you get a probability distribution labeled by the B's, and the very least you want that one of these things happens, so that these things the contraction should add up to 1. And then you form the I know it's standard to write AB XY, but it's really, you know, the AX BY coordinate of this matrix is the, you know, you apply your, you know, you compute this operator applied to this unit vector and take its inner product with the unit vector. So, right, so you compute the value of the state at this operator, and this gives you a number. Okay, and the number line winds up landing in 0, 0, 1. And okay, so the collection of all of these things forms the set CQ of NK, and you don't actually want to look at that set by work of Slofstra. You know that set is not actually closed, so you want CQA, which is the closure of that set. CQA of, and for N and K, right? So for any fixed N and K, you get this set. All right, so okay, hopefully this doesn't differ too much from what was said on Monday. And this collection of positive contractions that sum to 1, these are called positive operator valued measures. Okay, so instead of writing all this later, I will just write POVM. Okay, so I want to just grab one piece of this long paper, MIP RE, and I want to try to convince you that this is the form that we need it to apply continuous logic to. So here's a theorem in the paper by Chi, Natarajan, Vidick, Wright, and Yuen. If I take any Turing machine, and any epsilon greater than 0, usually you would think epsilon is a half or something. It doesn't really matter, at least for what I'm saying. Then I can explicitly find numbers n, k, and a linear functional L on the set of this quantum correlation set. So they're all given effectively. And of course, they all depend on M, right? Such that if I compute the supremum over all P, all the nk by nk matrices in CQA, and I compute the absolute value of the this linear functional applied to P, I'll get 1 if M halts, and I'll be epsilon away from 1, so I'll be separated from 1 by at least epsilon if M doesn't halt. Okay. Now again, this warms the heart of a person working in continuous logic, because this feels exactly like the kind of thing that you want, that you want when you're doing, when you prove anything. We know that it's not good enough to know that something's not 0. You have to know how far it is away from 0, and so on and so forth. Okay, so even right off the bat, this feels like it might be something that is helpful. Just so that I don't have to keep repeating this formula, I'm going to call this the indicator function. Okay, so I'll call this formula sup sub p of the absolute value of L of p. I'll call it the indicator function. Okay, and what's it actually indicating? It's indicating whether the Turing machine is halting or not. Okay, so aren't we done? Didn't I just write down something in continuous logic? Yeah, of course, the halting problem is undecidable. So if that was really straight up a sentence in in continuous logic, and universal sentence in continuous logic, then the theory of R is undecidable. Okay. Well, okay, it's not quite that easy. It looks very close, but it's not. So let's look at a few things that you have to worry about. Right. These are all the good things, right? The form of the indicator function is the right thing, right? I mean, the absolute value of a linear functional defined on nk by nk matrices, this is going to be a perfectly good function. You're taking the supremum over some set. Okay, that set doesn't quite look exactly like the kinds of things that I was talking about initially when I was talking about continuous functions or continuous logic, but it is going to be the range of some something that we can define. It'll turn out. Okay. Right. So the set looks like it might be the range of something that we can get our hands on using continuous logic. There are some annoyances. There was a tensor product involved there, but dealing with tensor products is often difficult in this area. There was an arbitrary state thrown around. You had ambient Hilbert spaces and stuff like that. So there's a few things that you have to work out so that this. Okay. So let me try to. I don't think I'm going to be able to completely convince you of this, but let me try. Let's deal with some of the things that are easy to deal with. On the level of dealing with an ambient Hilbert space, this can be taken care of. The sentences we're going to write down are going to be in the language of Tracial von Neumann algebras. So we're always going to have access to the standard representation, right? So we'll have access to the standard representation from the language of Tracial von Neumann algebras. So the ambient Hilbert space, just having an HA and an HB, you can replace that with, L2, and that will be okay. All right, so the ambient Hilbert space won't hurt us. The POVMs are actually a quantifier-free definable set, which is nice. And so So we're allowed to quantify over those. Okay, that's a little technical. If you don't know what that means, then just believe me that the POVMs are not gonna hurt us either. States. Okay, so if I have a unit vector on, right, if my ambient Hilbert space is going to be L2 of m tau, then my state is going to look like, an infinite sum of a bunch of, Cn tensor Dn's, where the sum of the squares of the coefficients is 1, and I've got an orthogonal collection, right? So basically I'm just writing down, I take a orthonormal basis for L2 of m tau, tensor L2 of m tau. I just write it out, and I get this representation. And that's what my states are going to look like. Okay. There's a few things that are being said here, right? I've got an infinite sum whose squares is squares of these numbers is equal to 1. I've got things that are orthogonal as orthogonal operators in L2 of m tau, and altogether I want all of these guys to have 2 norm 1. Okay, so which of those things is problematic? Okay, we go on to another slide of not worrying. We're not going to worry yet. Okay, the infinite sum is not going to worry us because we're actually only going to approximate things. So if we do this approximation well enough, we're only going to need finitely many of these tensor products. You do have to bound the number of tensors you're going to use, but to bound within delta, the way we will do it is we will be able to bound the number of these elementary tensors that we need. Okay, so that's one thing. This is beautiful. I wish I was teaching a more advanced class this year. The demanding orthogonality in L2 of m tau is the Gram-Schmidt process, which is sort of interesting, right? If you take a series of things of trace 1, and then you start which is almost orthogonal, and then you apply Gram-Schmidt to it, you don't move things too much, and you'll wind up with stuff that's orthogonal. So it's anyway, for someone who teaches linear algebra from time to time, it was sort of fun to notice that this part really did use some trivial linear algebra. Okay, what do you have to worry about? Since you're working in L2 of m tau, right, you're giving up the access to the Hilbert space, but you have to worry about the 2 norm, right? The 2 norm is 1, but if I allow arbitrary things of 2 norm 1, I could have unbounded operator norm. Okay, so I do have to worry about this. I gave a practice version of this talk last week, and someone said, "Oh, so on the slide that we don't have to worry about, this is the thing you have to worry about." Yeah, okay, so this is the thing we do have to worry about. We do have to worry about it. But since we're approximating things, it turns out we can get away with a bound on the operator norm, right? So we're not going to be able to sample across the entire state space because you get unbounded operator norm for that. But you can get close enough with a bound on the operator. All right, so I want to make sort of, okay, sorry, yes. Sorry, I thought I was going somewhere else here. Let me try to, in the last 3 minutes, a relativized version of CQA. I said I want to apply this to any tracial von Neumann algebra. So basically, I redefine the notion of CQA relative to a given tracial von Neumann algebra. Okay, so we have our von Neumann algebra with its trace, and I just do the same thing. Only now I'm not allowing myself to go to range over arbitrary places where these operators act. I'm taking operators from N, both A's and B's, and I am looking at unit vectors on L2 of n tau, tensor L2 of n tau, and I'm computing the entries for the matrix at, at these operators applied to that vector. Okay, I take all possible matrices of this kind for n, and that's what I call CQA relativized to n. Now, of course, for what we want to do, I want to say that if I have, for instance, MP of C, so P by P matrices, I want to write CQAP of NK. So if I just look at what happens on P by P matrices, right, then I look at this quantum correlation set restricted to MP of C. Okay, and here's a relatively easy fact to prove, that if I take the ultra product, so here I did use a U, Aaron, I apologize. The ultra product of CQAP of NK, right? It's not that hard to see that you actually get CQ of NK, right? Because, well, certainly anything I get in CP of QA and NK will ultimately be something that would appear in CQA, right? But anything I get in CQ, QA, and C, so the quantum correlations, will appear approximately in the ultra product, right? So this ultra product fact is one important thing that's hiding behind the scenes here. All right, and then yeah, okay. So I think maybe I've got enough time to just try to give you a basic sketch of the proof. So we produce a universal sentence, right? Which, depending on the tolerance I'm given. So remember how this tolerance will come, right? This tolerance will be based on looking at, I'll take the MIP star equals RE result. It will give me a linear functional. It'll give me an N and a K and something. And I look at the uniform continuity of that thing that, I want to approximate to within something. So I want to approximate my domain to within some delta. So I'm going to want to get the correct value of the indicator function up to delta. I want to, I'll have to backtrack, but everything's explicit. So I backtrack to find out how closely I have to approximate those big summations or whatever. Okay. It is the fact that if I look at the indicator function itself, it actually is a universal sentence of continuous logic. That bothered me for a long time. It's just not something we can access effectively right away. Okay, so I produce this universal sentence phi delta that'll get me the indicator function to within delta, and then I compute this in all matrix algebras, right? And basically, I just look at the value of phi delta in the matrix algebras, and I take the ultra product of those matrix algebras. That gets me the value of phi delta in the ultra product of matrix algebras. But the universal theory of the ultra product of matrix algebras is the same as the universal theory of R. Right? If you probably already believe that, but that's easy if you don't, and to figure out. Now, if the universal theory of R were decidable, right, then we could compute this value to within delta in R. Why is that bad? That's bad because if I now take a Turing machine and I let epsilon be a half, I can use the MIP star equals RE result to compute NK and L, build my indicator function, figure out what sentence I should be approximating to within delta, where delta is going to be a fifth or something here. And I'm going to ask the universal theory of R to compute this for me. And it's going to come back with a number that's either close to 1 or close to a half. And I've asked it to give me the number to within a fifth, so there's going to be no overlap. So I'll be able to tell if M halts or not, right? Which is bad. So the theory, the universal theory of R is undecidable. Okay, I think I've gone a little over time, so I apologize, and I'll stop here. Thank you.
Well, that's glad for any questions?
I have one.
Mm-hmm.
I think you should look at our theory of asynchronous things. I think that would eliminate, that would make your proofs a bit shorter.
Oh.
What we show is if you look at these quantum correlations, we define one of these PABXYs to be synchronous. If PABXX is equal to 0 whenever A is not equal to B. And so that just defines a proper subset of these correlations given by this, this set of linear equations.
Oh.
And we've shown that CQA synchronous equals CQC synchronous if and only if Connes is true.
Ah, okay.
And then all of these we show come from traces. If you have one, then it comes from a trace on the C-star algebra. So you don't have to look at arbitrary states. It's the trace,
okay,
but varying the operators, the A's and the X's. Then what's interesting is in their proof, all the games they consider are synchronous games.
Ah, mm-hmm.
So I think there should be a radical simplification, maybe, if these observations are.
Okay. I will freely admit that over the last few weeks, while I've been trying to work this out in detail, I've actually considered sending you email several times as I read about your coloring papers and whatever. I just never quite knew what question to ask. So thank you for telling me what question I should have asked and answering it.
I've been exactly the same way. There's just so much in their paper. It's hard to know.
Yeah. I was just making sure that I wasn't, having some of this stuff depend too heavily on something that I had no clue what they were talking about. So anyway, yeah, no, it'd be great if there was a much quicker way to see that we could get the approximate state argument.
Also, you worried about the quantifiers of all Hilbert spaces, but can't you just restrict to the CN tensor CKs, and then for inside their unit spheres, you can just take a delta net, and so you really only have to consider countably many vectors in a countable family of Hilbert spaces.
Right. The formalism of the universal, like the way that the universal theory is constructed and its formalism, I don't have access to an arbitrary Hilbert space, so I was using the standard representation, but the standard representation doesn't come with the usual continuous logic Hilbert space structure. It comes from the structure that's inherited from the tracial von Neumann algebra. So this could be just an artifact of the logic we're using here, but
But I was referring back when you look at their your indicator function L.
Yeah.
It's really a soup over a countable set.
Yes, right. So as long as you can get access to those, like to a dense enough set of that, then it's yes. It's just formulating it in a way that it can appear in a universal sentence of continuous logic.
I see. I see.
So while we wait for more questions, so basically to recap, so you completely removed operator algebras from CEP. Now Verm puts us a little bit back, but you're saying it's completely logic problem, right?
Yeah, I tried. Okay, I have tried. I tried not like. Did I not say beautiful operator algebra that goes from Cyrildson to QWEP to CEP? There's a lot of rich mathematics in there, but if what you wanted was a beeline to the failure of CEP, you can get it from MIP star equals RE directly. That I guess that's what I guess that's the end. Here, can I had the slide for George. Can I get to this? Can I just pop this slide up just for fun? Because of course this is what. This is where the operator algebra would come back in, right? If we had a concrete counterexample to CEP, right? So can we construct a concrete counterexample to CEP based on this proof? No. No, this is the proof. This is the same style of proof that MIP star equals RE gives for to show that Cyrildson is not true. Right, assumes that Cyrildson is true and then contradicts what they can prove. So this is the same sort of thing. So of course, the failure of CEP just on its own is a bit unsatisfactory without knowing an example of a 2-1 factor. But just as I don't even know whether David Sherman, are you listening? No, okay. I just remind everybody that we know an example of a 2-1 factor that does this. It's the famous Sherman S. David claims that he used S because S was the next letter after R, but Ilias and I always joked with him that he was just naming this after himself. There is a 2-1 factor with the property that every separable 2-1 factor embeds into its ultra power. And, you can concretely get this by doing what I say in the last bullet point. I'm sure George is perfectly unhappy with this answer, but.
Have you taken a look at the trivial, what Henry was saying about the trivial Turing machine?
No, I haven't, and I did, I'll show you, I did write down George's question. Good question. I noted your question, George, and as soon as I get some time, I'll think about it. Yes, that's a good question. What if you just program up a silly loop? What happens? Yeah, I don't know.
So there is another good question on the chat from Marius Junge. I can read it if you want. Sure. So I have a question. Sorry. Is there a commuting operator algebra polynomial which is not decidable in some von Neumann algebra?
Poof. I honestly, off the top of my head, I don't know the answer to the question. The form of the sentences that we're using here are actually not that complicated. But I don't. Things are not commuting for sure in there.
Maybe I can be a little bit more specific about the question. So if you take the commuting operator model and evaluate these games with the commuting operator module,
right?
And essentially, you're evaluating this, for instance, in this S. You're finding some operators, and since using Vern's remark, they're commuting, you can take them from the commutant. And that is very much accessible to continuous logic, right? Because you have
it's
the
true.
So this means in this S, you could ask for the same games. And is there a game which is not decidable inside that theory or inside that von Neumann algebra? And that is, so this would be another theory because by your result, we know this is not the same theory, right? So these things don't have the same continuous logic and would be very interesting. I think this is related to also a question by Henry Yuen, whether that monster has also undecidable, is also undecidable. And I think that is related to the other question Henry had. MIP equals co-RE. I mean, I don't remember the exact.
Oh, I see. Right. The MIP co-RE.
Yeah. So that would probably asking a similar question with commuting instead of tensor product gains, right? So in the strategies, you have to use the commuting operators from the commutant. And since you're using synchronous gains, it's really, the commutant. You don't have to do a tensor product or anything. It's a commutant, that's all. And then you would try to ask whether such a game, for a game, you have a certain polynomial, which you need a certain state, which has value 1 or not. And that is the question you're asking for. Is that a decidable question?
Okay.
It would be very nice to know whether S also fails that property.
Right.
I may be missing something, but we are talking about universal theories being undecidable, and they're all the same.
Yes,
No.
but
no, they're not. They're not. Ask a different one. Yes.
The one you're staring at right there, Ilias, does not have the same universal theory.
Yeah.
But it would be interesting. Yeah, it'd be interesting to know if they all had the same. If all the universal theories, so. To be honest, what we initially started to do was think about whether we could construct any 2-1 factor with an undecidable universal theory. And then, of course, the natural question became, what about R? And then, then you could ask, well, okay, what about other 2-1 factors? Maybe they have decidable theories. Well, that sounds very unlikely. But maybe you could make a distinction for commuting or particular fragments of the universal theory. I don't know.
Actually, these non-local games give you rather explicitly some kind of sensitive which you want to check on decidability.
Yeah. Okay. Thank you.
Do we have any other questions?
I have a quick question.
Yes.
So, I mean, this is probably wrong because the logic is different. But suppose you have a group with undecidable theory, then what about the group Von-Neumann algebra?
Right. So the easy answer is it's very unlikely that just ordinary classical behavior of, say, the word. So if you're thinking universal theory, then you'd be thinking like the word problem. If you have an undecidable word problem in your group, does for group G, which is the right kind, then does L of G have an undecidable theory? That's unlikely. But if you think about the rigidity results, can you find various rigid or super rigid groups with undecidable word problem, and then is there something about the universal theory of L of those G's that you can read off, undecidability, and maybe that's maybe that's another way to see, because most of these L of G's are actually R omega embeddable, so maybe that's another way you would see that the universal theory of R is undecidable. Although, yeah, I mean. You have to code something. You can code the word problem for the group. You try coding Turing machines directly. Something has to get coded.
Is there just one S, or is Sherman's S? For some reason are they all the same?
No. You can find lots of. There's nothing wrong. So if you look at the quote construction that I give you there, you could throw any extraneous amount of stuff in, add it as a free,
Well, okay, so it's not. That means it's not obviously unique. It's obviously not obviously unique, but
no. What is unique is its universal theory.
Yeah, but can one actually deny? I mean, can one produce 2 S's which one can then prove are non-isomorphic?
Yes.
Oh, okay, thank you.
Yeah.
Well, the reason is Ozawa's, if I can, Ozawa proved that there is no universal 2-1 factor. So S, I mean, no matter what you choose, it's not going to be universal. So they're actually going to be continuum many S's.
There'll be lots of S's.
Okay.
Or another way to see it is that from S to the omega, you could take Well, from S the omega itself, you could take any elementary submodel that contained S, and like there's going to be lots of them. What's unique about this is that there's a minimal universal theory. If you know, of course, if CEP held, there's only one universal theory, so there's a maximum and a minimum. But now we know that the theory of R, the universal theory of R, is a maximum, and there is a minimum, and right, and so anything that satisfies that minimum theory could be S.
What about the trivial whatchamacall? The trivial Turing machine, could that could
be something that satisfies the theory of S, but I don't think you would. It would be amazing if the way that you prove that this is what you do is you embed, you build a 2-1 factor like that, and then you embed every other separable 2-1 factor into its ultra power. That would be quite a proof. That would be quite a proof.
Well, okay, but there are surprising things. For instance, the Poulsen simplex is quite surprising.
Yeah, no, I don't deny that. It's just
I'm sorry for introducing a speculative note.
Okay.
I have just one quick question.
Yeah.
Can you use this deformation rigidity fact that comes into play to show that there are uncountably many undecidable theories?
It almost certainly has to be true. It might even just be true from some kind of purely, because I didn't say that, because I only needed one direction of what Isaac and I proved in this earlier paper, but we actually proved that CEP was equivalent to all universal theories of 2-1 factors were decidable. Of course, we were trying to prove that that CEP was equivalent to the universal theory of R being decidable, but we couldn't prove it. But there can only be countably many, if they're all decidable, there can only be countably many because you don't have that many algorithms. So if CEP fails, there should be lots of at least tracial von Neumann algebra. Whether you can make them factors or not, I don't know. But could you do it by building lots of examples of super rigid groups and looking? I don't know. And it is something that people like Ionitz, Kifon, and others have looked at. So I don't know. So
I think it is true that that these super rigid groups are all Sophic, I think. So maybe I may be wrong, but so they definitely embed into R omega.
Oh, the super rigid ones.
Yeah, the super rigid ones. But
right, but yeah. So, but if you could have a super rigid one with an undecidable word problem, that would be the one that you would want to be thinking about.
Well, actually, I may be wrong. So just
okay.
Yeah.
Okay, there is a comment from Ben Hayes, not sure about that last part. I agree, but Ben, do you want to say something more?
I'm not sure whether the super rigid groups that are constructed are Sophic, that's all.
Okay.
Because you take Reith products but you don't take standard Reith products, you take like Reith products over, I'm not sure like the stabilizers in the Reith products that you're taking, these generalized Reith products with respect to are amenable, for instance. Like, I don't know if you're amalgamating over non-amenable things at any point, anytime you leave something like Reith products or free products and you don't do them with respect to amenable.
Sorry, I was being naive. I just thought they were Reith products and I just said they were Sophic. So sorry.
They're not straight up Reith products though. They're like generalized Reith products. And if the stabilizer subgroups aren't amenable, then the whole game is over. So I don't know.
Yeah, I think it is a good line of inquiry to try to understand the relationship between the word problem in a super rigid group and its related theory, universal theory, the theory of L of G for that G. That's, I mean, yeah, because I think lots of people say, can't you just code the word problem? Well, okay, I mean, you lose a lot when you move from G to L of G, but that's the whole point of the, you know, the super rigidity. If you try not to lose G.
Yeah, well, I completely agree, but also, you know, just every attempt to use Lil Celas result that all the FNs are elementalities. I mean, it's basically everything, all the discrete first order theory of group disappears when you move to L of gamma. So
no, right. No, so yeah, the FNs are not good enough for this. Yeah. There's other results of Celas though that are intriguing in this direction, just sort of like trying to compute limit theories of particular 2-1 factors, even the universal theories. And yeah, if I had an infinite amount of time, I've asked Salah about this himself, and he doesn't see any particular reason why some of the things that he did in the discrete case wouldn't go through in the continuous case. But I don't know how much continuous logic he knows. But